Good morning, my name is GOS. Welcome back to Geo-Hikes. This is episode 2. We're here at the Southern Franklin Mountains. So I want to go over a couple of the issues that we were facing last week. We didn't have sound. Yeah, I mean, the camera was a little too high at times too. But we'll be doing a potential collaboration with a couple gentlemen from Geo Ventures, and we'll hopefully be doing not only a drone study, but using this camera, we'll be doing a walking the fault trays study as well, looking for slick sides and displacement and stuff like that. The format going forward which is this first portion, and it's something I always did in my undergrad, was I researched the area that we were going to, so I wouldn't be surprised at any rocks that I would come across. I would be mentally prepared as to what type of rocks, I could come across. And that's something that I learned to do while at university. The second portion of this format is the hike and field work, which is the meat of the videos, and then the third part is the discussion. We'll discuss what we saw throughout the hike, and then I'm going to post a Wylin hike disclaimer now. And I was able to get permission to do this hike. The Wylin aerial tramway is technically closed, unfortunately. It's one of my favorite hikes in El Paso. But if you want to hike this, you have to get permission, or you have to go on one of the guided hikes that they do at the end of each month or the beginning of each month. We're doing the Southern Franklin Mountains. I'm going to citate the research that I used to research the area and to kind of get a description of what we'll be seeing, which is Geology of the Northern Franklin Mountains, Texas and New Mexico by R.L. Harbor in 1972. It's kind of dated, but it's good stuff. It's a good read. So we'll be seeing the Red Bluff granite, youngest Precambrian rock in the Franklin Mountains. And then after that, we'll be seeing the Bliss sandstone, which is late Cambrian Ordovician, early Ordovician in age. And then we'll come into the felsite sill, which is actually the youngest rock in the section, but it's like smack dab in the middle of the section. So that'll be interesting to see. And then we'll be going into carbonates, the El Paso and Montoya groups. They're both Ordovician in age. And we'll talk more about that as we get up there.
I was pointing out scolithos, which are those little, well, not really little, pretty decent sized bullet hole looking things. They're called scolithos, basically worm burrows. I point them out throughout the hike, throughout the hike through at least the Bliss sandstone. So the Bliss sandstone was believed to have been deposited during the mid Ordovician? No, wait, sorry. Late Cambrian or early Ordovician. And that's what determines the span of time between the Red Bluff granite and the Bliss sandstone, the Great Unconformity, as it's known. It's believed to have 500 to 600 million years between it. So when I was hiking this, I was talking about that. I was talking about the Bliss sandstone does contain clasts of the Red Bluff granite, which means that obviously the Red Bluff granite is older based on the principle of inclusions. I was pointing out cross laminations, which is indicative of the Bliss sandstone. I was looking for it, and then I finally found them in this portion of the hike, and they're actually pretty well preserved. I was surprised. Yeah, you can see them pretty well in that picture. Other thing that I was pointing out during this portion of the hike was the fact that there's the siltstone. It weathers into little flakes. The siltstone is interbedded within quartzite and sandstone. It weathers green, so And it weathers green because it has glauconite, and glauconite is basically algal poop. I mean, that's basically what it is. So when you hike the Bliss Sandstone, you'll see a lot of green, and that's what that is, and it's actually a really pretty color. Bliss Sandstone that's a characteristic of it, is it's very colorful. You have green, red, orange, brown, yellow. The yellow and red are from the iron in the rock that is being chemically weathered, and it's turning into hematite and limonite. Bliss Sandstone is pretty interesting to look at. And then the quartzite within the Bliss Sandstone is due to, well, typically quartzite is a contact metamorphic rock, but in this case it was probably metamorphosed through deep burial and just the natural heat that you get from burying a rock so deep. Very hard. It's one of the hardest rocks you'll come across, so if you take a knife to it, it shouldn't scratch. That's how you'll know it's the quartzite portion. Of course, sandstone is also very hard, especially if it's a mature sandstone. Sometimes it's hard to tell the difference between the quartz heavy sandstone and the quartzite. That's in contact with the felsite sill, which is actually the youngest rock in this section, as I will talk about in the next audio clip that actually recorded. So
All right, welcome back. We are at the top of the Bliss Sandstone. So this rock right in front of us is actually the youngest rock in the section, and it actually intruded between the Bliss Sandstone and the El Paso group. It is believed to be about the same age as what happened at Crystal Ray, the intrusion that happened at Crystal Ray. And during my research at Crystal Ray, I didn't realize that we had felsite over there in the southern portion of Crystal Ray. So that makes me realize that maybe there's a connection to this felsite over here. Then guess that that this intrusion probably happened before these mountains were faulted into existence and uplifted into existence. But yeah, this felsite is believed to be about 23 to 66 million years, which is a very large time span. But yeah, and felsite is basically an intrusive pluton. It's very heavy in your light minerals like quartz. So pretty interesting. But it's actually the youngest in the section, Tertiary in age. And funny enough, the Bliss Sandstone and the upcoming rock, which is a carbonate, El Paso group, it's actually conformable, which means it was deposited one after the other. And interesting thing about sandstones is those are typically deposited in cold oceans, whereas carbonates are deposited basically in shallow tropical. So I think that plate tectonism played a role in how these got deposited one after the other. There was a shift in plate tectonics, which probably moved this portion of the Earth towards the equator, and you started seeing a a shift towards more carbonate rock. And this is the lower portion of the El Paso group. You kind of see cross-bedding and all that, and it's actually a sandy limestone. So you kind of get basically a mix of the two, which tells you there's a transition between different depositional environments. You can see some cross-bedding. you'll see the transition a little bit Bliss sandstone, but it sharply transitions into sandy limestone, and yeah, that's probably due to plate tectonics and the plate shifting towards the equator, causing a climate change and allowing for deposition of carbonates. Pretty cool. So we'll definitely want to keep an eye on this rock, because I believe there's 3 portions. I'll have to look in my notebook, but I'm pretty sure there's 3 segments of the El Paso group, and then it goes into the Montoya. Deciphering where that contact is pretty difficult, but now it looks like we're through the sandy transition and into more carbonate looking, more limestone, I should say, looking rock. And one thing when you're identifying carbonates is you typically want to break the rock open with a rock hammer, but I don't want to be doing that out here, state park, all that. But you're going to be determining if it's micritic or sphaeritic. Tell you about where it can crystallize and all that. Sphaeritic tends to crystallize more near a reef, whereas micritic will form in the mud portions of a carbonate shelf. I'm not going to break a rock open though. And one thing when you're hiking and mapping, you want to look for soil color changes. It's kind of difficult to see here, but when you're in the foothills below a mountain, sometimes contacts are hard to see, but you can determine them by soil color changes. Soils are kind of wet right now, so kind of difficult to see at this point, but it's a helpful tool when you're out in the field mapping. So this carbonate doesn't look like it's fossiliferous, so you can add that to the description. And some of these, I don't even know what they're really called, but basically thin laminations within the rock that protrude out, that are weathered in such a way, maybe it's dolomitization that's causing that. But yeah, this is early Ordovician. This is tied to the Sauk Epiarch Sea, as I mentioned earlier. Interesting thing about the Franklin Mountains is we've had, and I can't count off the top of my head, it seems like 4 or 5 transgressions and regressions in our area of the ocean. Otherwise, how do you get carbonate rocks? Kind of looks like we're getting to a rock change. You can see it right here. It goes to that tan color, and it looks like the rocks have changed, so we're probably in the middle group of the El Paso group. It looks like the rocks have changed in color a little bit. I'll pull out the notebook just to verify, but pretty sure this is another portion of the El Paso group. So according to my notes, this is a far offshore carbonate in a shallow, turbulent sea. And supposedly where we see this gray rock across the way, we'll be coming across that. That's supposed to be containing angular fragments, which is evidence of a turbulent sea, because the reef was being broken apart by probably a sea that saw a lot of hurricanes and other tropical storms, other types of tropical storms. So pretty cool. We'll have to look for that. And yeah, it looks like we're in the middle group and we're about to pass into the upper group. It has a sandy base, but it's a fine grain, light gray dolomite, and it's finely laminated. Sometimes it's hard to see, you know, contacts between two carbonates. Hurricanes were breaking apart the reef that was built, and then they were re-cementing. So that's really cool stuff. This looks like it's in the upper member of the El Paso group. Starting to see some thin laminations. It's actually kind of varying between this tan rock and this angular fragmented gray carbonate. It's weird how the transition was kind of gradual. It kind of like interbedded, and then it turned into this gray rock that contains the angular fragments that they're talking about. This isn't looking too fossiliferous, other than what's on the surface, which kind of looks like it's a coral or some kind of fossil. Sudden change in rock. This looks like it's the Montoya contact with the El Paso group. This Montoya lower. I'll sit at the bench and describe it, but there's 3 units within the Montoya group. The Elman, the Upham, and the Cutter, I believe. So we're here at the El Paso group. We're about to cross over into the Montoya group, or Montoya formation. So the last 2 rocks that we went through, at least the Bliss Sandstone and the El Paso group, not including the felsite sill, those were deposited conformably with the Sauk sequence, S-A-U-K, if you want to Google it, look it up. Pretty interesting. This next carbonate was actually deposited during another transgression, which is called the Tippecanoe, T-I-P-P-E-C-A-N-O-E. A different transgression, which happened in the Middle Ordovician. It's pretty interesting. That's already evidence of 2 different oceans in this section of rock. That's 2 in the Franklins, and then there's like 3 or 4 more that have happened, at least in our area, not just including the Franklins. So yes, we are about to cross into the Montoya, and so you have the Upham, the Elman, and the Cutter. So I'll read the descriptions. They're very similar. It's going to be hard to determine exactly where the contact is, but let's see if we can figure it out. So the Upham is your basal unit, your lower unit of the Montoya. It's a medium grain gray dolomite. Your Elman is the middle unit. It's fine grain dark gray dolomite with layers, lenses, and nodules. That one should be pretty easy to determine because it has the lenses and nodules of chert. And then the Cutter is your top grain unit, which we'll see at the very, very top of this hike. It's fine grain, it's dark gray, it's evenly bedded. There's not very many chert nodules or lenses. And overall, the Montoya was believed to have accumulated far offshore in a calm tropical shallow sea. So we won't see the angular fragments cemented together in the Montoya like we did a little bit. Well, we might. So it's the difference between the 2 oceans. It was probably not completely, it was probably more tropical, I would guess, in an area where that doesn't get as much hurricanes, but still near the equator. So probably similar to the west coast of the United States. Maybe, I don't know. Yeah, let's get rolling and figure this thing out. Look at some more rocks. That kind of looks like it's a stromatolite with how it's mounded like that. And just in case you guys don't know what a stromatolite is, it's one of the, well, it's built by the oldest organism on the planet, which is called a cyanobacteria or a blue-green algae. They create these little mounds, layered mounds of mud and carbonate, and they're called stromatolites. That's what that kind of looks like. I've never actually found one in the field, so that would be cool if that was one. That's pretty cool. All right. Actually, I just wanted to point out from here, you can see the southern Franklin Peak and northern Franklin Peak. Not so much northern Franklin Peak. It pokes out off in the distance, but you can see southern Franklin Peak pretty well from here. It's a good view of the Hueco Bolson. You can't see the Hueco Mountains. It's a lot of moisture in the air. Maybe there's a forest fire. I'm not sure what's going on today. It's nice and breezy, but all right, let's finish this hike off, because there is a regression at the end of the Tippecanoe, and then there's another transgression after that one, which in the northern Franklins, I believe it's the Kaskaskia is the next one, but you don't find evidence of the Kaskaskia in this section of the Franklin Mountains. That's a more Pennsylvanian rock, which you see in northern Franklins. So if you guys don't know how to tell the difference between a limestone and dolostone, drop hydrochloric acid. If it doesn't fizz right away, then pulverize the rock, which I'm not gonna do, but pulverize it and then drop that hydrochloric acid on the powder, and that should fizz. That'll mean it's a dolomite. And really the only difference between the two is one has calcium, which is the limestone, calcite, and then the other has magnesium. Sometimes carbonates can contain the iron to replace the calcium, and that'll be siderite. Yep, and here's another rock change. This looks like it would be the Upham. It's a dark gray, kind of marl is what they call it, marly looking limestone, which means basically micritic, very fine grain, but it has a certain texture to it. So that's what that appears to be what we're looking for in terms of the Upham. Maybe the middle is a lot thicker than we thought. So this is the top of the trail. This is that Marley Upham. So we ended up being right. The middle unit was just a lot thicker than we had researched. Nice breeze, very nice breeze. It's always breezy up here, it's nice. That's the west side of El Paso.
Angels sent from heaven showed me how to think. can see the ground. Can we stop this gravity? It keeps bringing me down.
That breeze is nice. Whew, that's cold. Okay. So, probably start heading down. One thing I'd like to say is this looks like fenestral fabric, which is basically algae farts. It's a muddy, this means shallow carbonate shelf, and algae lives in the shallow carbonate shelf, and they let off a lot of gas, and it creates these little potholes that you see all over this rock. That's what that looks like. I'm not sure. I know you see it in the Fusselman dolomite, but here, that's what it looks like. Is that fenestral fabric. It's pretty cool. This is also described as a light gray marl unit. Yeah, this is the Upham, guys. Got a little confused on our way up here, but we got it. So we'll be heading back down now.
What's going on, everybody? Welcome to the discussion. I was finally able to get to it. I'm out here in the panhandle of Texas, about to head back home tomorrow. So I'm basically going to discuss what we saw, or what you can see at the Wylin hike. For some reason, it refused to record certain parts, especially the Great Unconformity. But what I will do is talk about, okay, so we had the Red Bluff granite, right? And then we had the Bliss sandstone. You have the Great Unconformity separating the two, and 500 to 600 million years of missing time between those two units. And it's an interesting thought to try and interpret what was happening during that time. Maybe you figure that the Red Bluff granite was exposed due to lack of depositions or erosion. Most likely erosion, because the Bliss sandstone contains fragments of the Red Bluff granite within it. So it's an interesting thought experiment anyways. I took some pictures and I'm gonna kind of go over those, and then I'll kind of go over the geology, the overall geology in this particular area. So these first two pictures that you'll see that will be popping up here soon will be quartz crystals that I pointed out in the Red Bluff granite. As you get closer to the top of the magma chamber, which was the Red Bluff granite, it's an intrusion, it's an intrusive rock. It would, the quartz crystals were going larger. It's because differentiation is going to be more extensive towards the top of the chamber, and that's where it'd be coolest, which would allow crystals to grow. And then in this next picture, this is the contact between the Bliss sandstone and the Red Bluff granite, also known as the Great Unconformity. And this unconformity, like I was saying earlier, this represents a time in which there was probably erosion, probably due to an ocean, because the Bliss sandstone has characteristics of a beach sandstone. There's probably an ocean eroding sediments or rocks that were above the Red Bluff granite. There was uplift, and it exposed the Red Bluff granite to the surface, and that allowed erosion of the Red Bluff granite to eventually create the Bliss sandstone. There is no exact explanation as to what the Great Unconformity is, but that's what my guess would be. So in the hike, we also see the Bliss Sandstone, and I have a couple pictures that show scolithos, which are basically worm burrows, which is even more of an indication that this was a beach sandstone. And then you see another portion, which there's 3 portions of the Bliss Sandstone that kind of alternate. You have this green siltstone that's interbedded within the sandstone and quartzite portions of the Bliss Sandstone, and it's basically due to glauconite, which is, like I said, algal poop. I mean, it's the simplistic way to put it. Gives you this really pretty green color. Yeah, I mean, even that's from algae, and algae form in the shallow portions of the ocean. Not form, but they live in the shallow portions of the ocean. And then I have other pictures. I found it interesting that we're seeing these sedimentary structures within carbonate rocks, and that's probably due to the inclusion of sands within the carbonates, and that would allow for cross-bedding and cross-laminations and laminations, such as you see in this picture. One of the cool things is I kind of guessed that it was a stromatolite that I was looking at in these couple pictures that I'm about to show. And it is a stromatolite. It has that layered, mounded look to it. I had never seen one in the field before. I finally found one. That was cool. And then this next picture, which the stromatolite I found in the Montoya. These carbonates are out of order because it's kind of hard to tell. I know that this one as well is from the El Paso group, because it has that fragmented angular fragment that was re-cemented, because the El Paso group was not as calm as the Montoya during deposition. So you had hurricanes, tropical storms, constantly breaking the reef rock, and during the deposition of the El Paso group, early Ordovician. So, and Montoya was later Ordovician. And, yeah. So we'll go through the geology real quick. Basically, we had the Precambrian red bluff granite intrude into the rocks that were there before. And those were eroded during this unconformity, probably due to an ocean. You had the Bliss Sandstone deposit over the red bluff granite, and it's derived from the red bluff granite, which is why it has its coloration, why it has fragments of the red bluff granite within it. And then you had the El Paso group deposit pretty much simultaneously with the or at least afterwards, right after, conformably deposit after the Bliss Sandstone. You had the El Paso group deposit, and then the Montoya deposited after an unconformity. And the El Paso group and Bliss Sandstone deposited during the Sauk sequence, and the Montoya deposited during the Tippecanoe sequence. So you had two different sea transgression and regressions, and then you had the tertiary felsite cell, that's a huge portion of missing time between the mid to late Ordovician and tertiary. But I mean, the felsite sill, which is the youngest rock in the section. It's smack dab between the Bliss Sandstone and the El Paso group. So just in this little area, you get a variety of different rock types, a variety of ages, and this one would probably end up being a 3-part series discussing the Franklin Mountains. I want you guys to appreciate the Franklins as much as I do now, knowing geology. Thank you for watching. See you guys next time.